Hello, my name is Pavel Butsykin. I'm from Virtuozzo. In this presentation, I would like to talk about the Prefetch cache, about the implementation Prefetch cache in QEMU, about what problems had faced during the development process, given characteristic of the block subsystem QEMU, and what result it led. To begin with, let's clarify what is the Prefetch cache. The basic idea is that we can read large data block before it is needed in the near future. There are different types of the implementation of the Prefetch cache, and main difference between them is method of defining location of the data that some might need. For example, the Windows Prefetcher, which remembers a readable area of the disk and use this information for following start to speed up OS boot. But in this presentation, we focus on prefetching sequential data read, and also sometimes called readahead. But in my opinion, it's just a variation of the cache prefetching. So, if for each read request we will read large data block, it can improve performance for sequential read data in small chunks. But also it can reduce performance for other cases such as random read. When random accessing, readahead can only increase load on the disk, but real benefit will not, because the cache will get data blocks that are almost never read from the cache. Even if we have only even if will be sequential read, abundance of random requests can will be displaced useful block from the cache, and but those additional and useless prefetch requests can affect performance. For success operation of such type of cache, we need to detection sequential read data, and only in this case to do readahead. This implemented master readahead caches, for example, in Linux kernel, and this approach is applied here. The implementation, some additional caches in large project may be controversial decision, because on the one hand, it could be useful features which can improve performance for sequential for the block subsystem QEMU. On the other hand, it could be a difficult mechanism that can add additional changes and also bugs. QEMU has a multi-layer block subsystem that allows to embed it between some block layers, and thus implemented block driver filters. The cache implementation in form of the driver filter will resolve mentioned problem, because we will get isolated piece of code which can be enable, disable, and without any changes in other components of QEMU. The best place where can stand pcache is between layer of virtual devices and layer format drivers, because pcache is aimed to optimize request coming from the guest, it can't account some features of format drivers. Also, sequential read from the guest doesn't mean sequential read from the file image, because image format can have some own cluster addressing, like a CO2. And so data in file can has a different order. In the guest, we can have some threads with sequential read, but for the block subsystem, QEMU and cache, it can look like a random read. Even if we have only one thread with sequential reads, the guest can have a lot of things that can generate many requests, and so for the block layer QEMU, it's also look like a heap of mixed requests. So we need the solid way to detection sequential read. And this way is pull request based on read block tree. Sorry, read block tree. The idea is that we keep statistic of requests coming from the guest. Just in fact, we add node in tree, and node description is just offset and size of IRG request. And, the pull request has a limited size, and the size limited by principle first in, first out. But node has a small size, and so we can keep a large number of requests. For the cache, our goal is detection sequential read, and for this we do request to pull statistic to found the sequential IRG request by length, for example, 128 kilobytes before current request, and if returns the positive result, we can do assumption the current request is sequential, and then we can do read ahead. But of course, not fact that request is sequential, but the cache is aimed to optimize typical behavior of the guest. In most cases, sequential read will be identified correctly. By technical point of view, request to pull statistic is just a search in tree where k is offset and size of range for which can be found some nodes. And the search range can be belonging multiple nodes, can be belonging only one node, can be no one nodes. Also note that not all requests come to pull statistic. For example, because filtering large requests, because the cache just can't optimize large requests. Let's look at the main stages of handling of read requests. And the first stage is filter large requests. If request more than 64 kilobytes by default, the request just skipped and goes to block level below. The second stage is update request statistic. If the request skips the filter above, and then in any case request come to pull statistic. But about this point I had taught in previous slides. By the next point we try raise data from the cache, and because requested data can already contain in the cache. And next we can have three cases. It's cache hit, partial cache hit, and cache miss. The last stage is read ahead, which include check sequential data and read into cache chunk of data from end of the current request. What does the cache memory? The cache memory very similar to pool statistic for storing statistic of request. Cache memory also based on read-block trees, but here Node has a touchy chunk of memory which contained data from the disk, and K describes location of the data. In most cases, node size will be equal readahead size, but in some rare cases, node has a smaller size. For example, when part of readahead already contained in the cache, we just cache the missing data, the missing piece of memory. The slide show an example storing a chunk of cache in view of tree and in view of that memory. But it is not real example working per cache because but just different variation node for simplified understanding cache memory. Actually, very hard to do then because become very fragmented. The cache memory has a limited size, by default 4 megabytes, and the size limited by principle LRU. But why LRU? Ask you. Because the cache is no type of cache, it could be useful LRU. LRU is only need for one. Allow reading node from the cache if part of node has been reading. Because there are possibilities, and after reading part of node, the node can be displaced, but it's not very good because we lose the necessary cache, which actively used, and therefore to hold actively used node, we just move it up the list. Of course, is we have an active process displays nodes, and we hold the last node will be displayed next useful node, and the hold last node doesn't make sense. But it's not true, because if happen unread node, the cache could get extra nodes, and so hold actively used node will be quite useful. Also, node have a counter which counted on size of data reading from the cache, and when counter became more than node size, then node is removed. It will allow effectively use the memory resource. Partial cache hit. With full cache hit, all cache miss is all clear. But what do we do if happen partial cache hit? The slide show two example of reading read request. On the one hand, large part request can already contained in the cache, and we can raise it. And for other part of request, just make new request. It can make sense. But on the other hand, request can hit to fragmented cache. And in this case, raise small chunk of memory doesn't make sense. It's just can't optimize request for SSD, but in some cases can optimize request for HDD. So for the missing data into cache, we just cached missing chunk of memory, and very fragmented cache happens in rare cases. Pcache is aimed to optimize read request, but write requests also need to handle it, because if happen write request to cached region, then data into cache become irrelevant. For solve the problem, we can drop all nodes intersection with write request or do write true. The implementation write true is a bad solution because it increase chance of very fragmented cache, and in some cases it can increase cache hit. Very great cases. One of the main point implementation Pcache is organization request completion. The request can come faster than much faster than I execute, but what to do if requested node is in flight? Of course, to wait, but then can happen situation where for request completion need to wait completion 2 or 3 other requests. For organization management, handling parallel of sorry, for organization management parallel of handling request completion was implemented the ability to creation communication many to many between the request and cache node. To implementation such a type connection, the request has a list of nodes which need add entry as part of cache. Also, node has a list of requests which need to wait request completion. Also, node has a status. It help handling and help to resolve handling requests. For example, if read requests cover node which in flight, then request just wait node completion. But if read request partially covered node which in flight, it is equivalent partially cache hit. When all node belonging to request will be completed, then the request will be completed. A little more about the request completion. Request and node have reference counter, and for request, ref counter is counter of wait nodes. For node, ref counter is counter of object which using this node. Such of object can be request or tree of nodes. If reference counter of request become 0, the request is completed. If reference counter of node become 0, the node is removed. Now, node completion can be described as decrease reference to node, which can be decreased reference to request. Request completion can lead to completion all new nodes belonging to requests, and node completion lead to dereference all requests pending completion these nodes. And so request completion for one node can lead to completion many. Sorry, request completion for one request can lead to completion many node and other requests. The last stage in handling your request is readahead. First, note that all request coming from the guest not cached, but used to store to update statistic of requests. Because cache is aimed to optimize the pattern sequential read data, it just doesn't make sense try cover other vector optimization, because for this there are different types of caches. Readahead is done only by the condition if before current request there are sequential read data enough size. This information can get pull statistic of requests, but of course this method detection is not very reliable, but in most cases it will work. Also note that if part of readahead already contained in the cache, we just cache it the missing chunk of memory. The slide show result uncached read test, which cover different pattern sequential different pattern read in small chunks by 4 kilobytes. It is random sequential read. It is synchronized, asynchronized with 1 for 16 threads, is in queue in 4 and 32 requests. The test will run on SSD to avoid slowing accessing to different parts of the disk. And the test present comparison result for the R4 configuration. In first column, this is base configuration with QEMU 2.6 virtio and Go2. The second column to base configuration at data plane, which allow in additional thread IO handling IO requests that in generally it can speed up IO handling. Here we can see about 40% performance increase for the test with asynchronized sequential read data with queue and 4 requests. And for the same test, but with queue in 32 requests, happen a small overhead. But in general, we can see positive changes in performance. Third column is base configuration plus pcache. There we can see improved performance for all sequential read tests. And result of random read test also reported, because their performance doesn't change. It is very good at expected result. In first column, combined data plane and pcache, and it get a good result. First, about 30% improved performance for synchronized sequential test, and second, left negative effect of overhead, because now most part of request hit to the cache. Small but positive effect of pcache was when directors read. The test iterates through the tree of directories in total size and 1,000 directories and 1,000 of files. By test result, in average, recursively walking directors tree with pcache by 2% faster. This effect happened because when walking directors tree, some file system blocks can be placed sequentially. And so, pcache can speed up search in file systems. QEMU I utility that is included in QEMU has option bench, which allows quickly and easily test our performance. Just for fun, I decided to test IoT requests, and this pcache show big increase in speed, but with increasing length of queue, the difference becomes less and less. But this that even with pcache and with queue in 64 requests, pcache test run a bit faster. The slide shows a histogram which describes requests asynchronized sequential read by 4 kilobytes coming from the guest obtained by Belka trace on the host. Red means request with clean configuration QEMU, and green means request with configuration QEMU pcache plus QEMU plus pcache. And there we can see all requests by 64 kilobytes, because readahead size 64 kilobytes. It is in general it is expected result. More interesting result we can see if compare configuration pcache and configuration pcache plus data plane. Red marked QEMU pcache, green marked QEMU pcache plus data plane. As we can see, requests by 64 kilobytes in configuration QEMU pcache plus data plane. By 20% less, because this request shift right in direction of large request. Just because thanks by your thread requests faster delivered into kernel, where it is merged in in a request of large size. So Pcache can optimize certain IO pattern without PCMizing other. Pcache implementation in form of the drive filter is universally, and Pcache is not a generic cache. So because the guest can have own readahead cache, and also the host can run the cache. And before use Pcache, we need to understand the cache can optimize our target. And also note that recently, at the morning, I sent RC version Pcache, and so you can look at the patches. So now, any questions?
Hi. I was wondering, did you run your benchmarks against cache equals write back so that we can compare it against the Linux kernel's, buffered IO read ahead? Because the Linux kernel can already do read ahead for us, but we would need to be using cache equals write back instead of cache equals none. I think that would be an interesting benchmark just to see what you're doing different. Because if there's not much difference, then it seems like what users should be doing who want this is they should use cache equals write back instead of adding this to QEMU, if you see what I mean.
Yes, Linux kernel has readahead caches, also, but these caches attached on FD, file descriptor. And this can't, but Pcache placed on some block layer above, and this can optimize more cases. For example, the search in directories tree. And of course, I agree that Pcache can improve performance for synthetic tests, but in some rare cases, it can optimize requests for live tests. But I think it is point from which we can move above, and implementation and test and implementation more other tests.
Okay, I had another question, and that's about request merging, because the virtio-block device can merge read requests. So when you did your benchmarks, if the virtio-block device receives multiple sequential IOs on the virt queue within a single kick, so when the handle function gets called in QEMU, and it goes through the virt queue, and it sees multiple requests, it can already do merging. And what can happen is that the benchmark inside the guest might be configured with 4 kilobyte request sizes, but when you look on the host, it turns out that QEMU actually converts that into larger reads. So I was wondering if you noticed that, because I think it's enabled by default. So that can sometimes affect benchmarks. That can sometimes interfere. Because if that happens, then what happens is that your Pcache will be getting different request sizes than what the benchmark inside the guest is trying to do. Do you see what I mean? Because the virtio-block device will merge the requests into bigger ones if you have sequential I/O. So often sequential I/O is not a good benchmark for QEMU because we mess with the request pattern.
Yeah, maybe right, but I also note IO thread can parallel handling IO requests, and it can speed up the lift request to kernel, and it can help merge requests. Because without IO thread, I get doesn't merge requests obtained by Belka trace. And also I have noted on the host, if we run only one VM, we can use cache, it will be okay. But if we have many VMs, the host caches will be always displaced, and usually cache on host disables. And for this case, maybe useful pcache. And
yeah, I was wondering if C groups can do that. If C groups can say this process or this group of processes have a certain amount of buffer, like page cache, that they can use.
Yes.
That way you can isolate them so they don't have this problem that you're mentioning. But I haven't tried it. I don't know.
Yes, thank you for questions. I will think about it. And also I sent RFC version pcache, and we can discussion about this. Thank you for questions. Thank you all.